Hello and welcome to Bitcoin Explained, where I break down some of the more technical aspects of Bitcoin in a simple way. In this video, I'll be teaching you about Bitcoin's curve, meaning the elliptic curve that Bitcoin uses, which has certain parameters and looks and works a certain way. This is actually the fourth video in a 5-part series on the cryptography behind Bitcoin. And previously we learned about finite fields, elliptic curves over real numbers, and elliptic curves over finite fields. In this video, we'll build upon all of that knowledge to talk about the specific curve that Bitcoin uses, and then in the next and final video, we'll talk about the elliptic curve cryptography and how you actually generate private and public keys and sign transactions in the Bitcoin network. Now, with all that said, let's talk about Bitcoin's curve. In this video, I'll be sharing my screen again. I've got a Jupyter notebook up here and I'll be walking you through a little bit of text and some formulas, and then also we'll be looking at some code, some visualizations, and the result of doing some operations on this code. This video is broken down into 3 different sections. First, we'll look at Bitcoin's curve, meaning the curve that Bitcoin uses. Then we will put the number 2 to the power of 256 into perspective and talk about why that's so important. And then I will teach you about private and public keys, which I touched upon in the previous video already. All right, let's look at Bitcoin's elliptic curve. So Bitcoin uses a specific elliptic curve. It's called SecP 256K1. And it's just a curve that's defined by specific parameters. In Bitcoin's case, or for SecP 256K1, A is equal to 0 and B is equal to 7, meaning that the form of the curve equation reduces to y squared is equal to x cubed plus 7. So that's the elliptic curve equation that we have here. And then there's also the order of the finite field that this elliptic curve is over, and the prime order of the finite field for Bitcoin is 2 to the power of 256 minus 2 to the power of 32 minus 977, and this is in fact a prime number. Then we have a generator point. Remember from the last video the importance of a generator point. This generator point for Bitcoin is the same for everyone, and it has the following x and y coordinates. This is the x coordinate and this is the y coordinate here. This generator point has an order. Remember again from the previous video, each point on an elliptic curve over finite field has an order. For the generator point, the order is this number here, which is a really, really large prime integer. Now, the x and y coordinates and the order of this generator point G here might look a bit unfamiliar to a lot of people who haven't seen hexadecimal number representation before, but we can also easily convert this into the integer equivalent or the decimal representation that you're used to. So there's different ways to represent the same number. You have the decimal representation, which is what we're used to from everyday math and the math that we learned in school. Then you have a binary representation, which is what computers use, which is just ones and zeros. And then you can also have something called hexadecimal representation, which has numbers and characters and is able to compress larger integer values more compactly. But if we just put these into Python variables and then print them, we actually get the integer values that they represent. So the x coordinate of the generator point is this here, the y coordinate is this here, and the order of the generator point is this here. Now remember that in the previous video on elliptic curves over finite fields, we had generator points like the point 518 here, which had an order of 37 because it could generate 36 unique points that all fall on this elliptic curve over this finite field, plus the point at infinity. Now 37 is pretty low, but we are dealing with a generator point that has an order of this integer value here, which is an astronomically large integer value, which also already gives you an idea of why Bitcoin is so secure, but more on this later. Now these are all just really large integers, and the same goes for P here, which we can technically also print using Python code. P, the order of the finite field, is just this number here. Both P and N are really close to 2 to the power of 256. In order to put 2 to the power of 256 into perspective, I've taken some examples from the book Programming Bitcoin by Jimmy Song here, which I can highly recommend. It's a really amazing book. But the examples go as follows. So 2 to the power of 256, first of all, powers of 2 are not something that we can easily imagine, comprehend, visualize, or even think about, because those aren't numbers that we're used to dealing with. So let's first convert it into a power of 10. 2 to the power of 256 is roughly equal to 10 to the power of 77. Now here are some comparisons. These are from the book. The number of atoms in and on Earth is 10 to the power of 50. This is so far away from 10 to the power of 77. So all of the atoms, the almost smallest things that make up everything around us and on this Earth, if you collected all of them and counted them, 10 to the power of 50. The number of atoms in the solar system, 10 to the power of 57. Still so far away from 10 to the power of 77. If you zoom out even further and you get the number of atoms in the Milky Way, that's 10 to the power of 68, which is getting closer, but it's still really, really far away from 10 to the power of 77, so way smaller. If you zoom out all the way and estimate the atoms in the observable universe, that will be 10 to the power of 80. Now that's finally a number that's larger than 2 to the power of 256, and it's actually a lot larger because we're talking 3 orders of magnitude here, but it really puts this into perspective nicely. Now another way to think about this in a way that you can maybe comprehend a bit more easily is, imagine if you had 1 trillion computers doing 1 trillion computations every trillionth of a second for 1 trillion years. Sorry, there's an E missing here. That number of computations would still be less than 10 to the power of 56. So let's think about this. Why is this important that both P and N, especially N, is close to 2 to the power of 256? For elliptic curves over finite fields, the elliptic curve discrete logarithm problem stated that if we do the point multiplication using a starting point, in this case this point here, and we then get an ending point, let's take 35 here, the only way to solve for this number 35, so to find the multiple of the starting point, is to brute force it. But if you're dealing with integer values, that can be the point multiple that falls somewhere between 1 and 2 to the power of 256, or roughly 2 to the power of 256, then the number of points that you would need to try out is so large that even if you were to do this many computations, you would only be able to try out a really, really small fraction, which is basically rounding to 0 or 0% of all of the numbers that you would have to try if you were able to do this many computations. Meaning breaking something or solving for an integer like the 35 here, if you're dealing with integers that can be that large, is computationally completely impossible. Now, let's talk about what private and public keys actually are. So, as I talked about in the previous video, a private key is in essence just a really large integer in the range from, this should actually be 1, this is not 0, in the range from 1 to n minus 1. Now remember here that n is the order of the generator point, and this private key is securely and truly randomly generated, and it has to be kept private. So only you, the person who generated this, should have knowledge of this, because when you then generate a public key using your private key, then you simply point multiply the generator point g using your private key, the really large randomly generated integer, and the resulting point q is then your public key. Really interesting. Now, let's actually look at an example private key and what the resulting public key on Bitcoin's curve would look like. Now, to do this, I have written some Python code. This is just using the finite field element class and elliptic curve class and elliptic curve point class that I've created in Python, which once again, in the video description below, there's a link to the GitHub repo where anybody who's interested in this and has some programming knowledge and especially skills in Python can use this and play around with it. But this is just to actually create the private key and public key. So first, I define the parameters of Bitcoin's curve, 0 and 7 for A and B, and then just create the elliptic curve. Then I create the generator point using P and the X and Y coordinates of the generator point, and then create an elliptic curve point. And then what I do to generate the private key here is I'm being a bit sneaky, and this is just for demonstration purposes only. Never do something like this in practice because it's really insecure. The private key in practice always needs to be truly, securely, randomly generated and never revealed. But what I'm doing here is I'm just converting the bytes of Satoshi Nakamoto into an integer, which is then the private key. And to then compute the public key, I just multiply the generator point using the private key, which is the integer representation of the byte string Satoshi Nakamoto. So the private key as an integer ends up being this number. As you can see, this is a really large integer number. And then when we point multiply the generator point with that number, we get the public key, which is just an elliptic curve point with the x coordinate of this and a y coordinate of this on the elliptic curve with a 0 and b equal to 7. But that's basically it. So the public key is literally just a point on the elliptic curve with an x and a y coordinate. Now there's a standardized way of converting this x and y, or this point with this x and y coordinate, into a Bitcoin address, which you can then use to go to a block explorer and actually look at the public key. Now I've actually coded that into the Python class for the elliptic curve point as well, and you can actually print the mainnet and testnet address by just running .address and .address with testnet set to true here. Let's actually do that and look at this in a real block explorer, real time. So the mainnet address belonging to this public key point here would be this. So if we then take the mainnet address that this public key point belongs to here, and we just paste that in a block explorer, like this one here for the mainnet, and we look for that Bitcoin address, you can see this is a valid Bitcoin mainnet address. It doesn't have any balance and it doesn't have any transactions. Luckily, no one has used this before. This is really insecure, so don't do this. But this just shows that you can actually generate the mainnet address. And then one thing we can also do is we can get this different testnet address belonging to the same public key, and then bringing this back in here. And if we go to the testnet block explorer, paste it in and look for it, we can see this is a valid testnet address, also doesn't have any balance and no transactions. So yeah, this is how private keys and public keys actually work in Bitcoin. And a private key in the end is just a really large and securely generated integer, and a public key is then just the resulting point of point multiplying the generator point, which is the same for everyone, with the private key. And again, the generator point is the same for everyone, and because we're doing operations over finite fields using modular arithmetic, everything is repeatable, deterministic, and predictable. So yeah, now that you've learned everything about Bitcoin's curve, you're finally ready to move on to the last video on elliptic curve cryptography, to understand how you actually sign a transaction using a private key and how you verify it using a public key. And then you will have understood everything that there is to know about elliptic curve cryptography, or the cryptography that Bitcoin uses. I'll see you there.